This call is now being recorded.
At the onset, I am actually having some glimpse of aerodynamics. Okay, as I mentioned in the earlier class, that as you guys are not accustomed to the subject of aerodynamics, we should actually proceed with some form of aerodynamics. And let me start my presentation. You see, there are some typical observations and typical assumptions of aerodynamics. Okay, be sure to have all these things in your mind for the next course of action. First of all, we see that if anything moves through air, anything, it need not be a flight only or a helicopter only, anything moving through air will have an interaction with the fluid elements of air, because air is actually flowing over this particular object. As an aerodynamic object, it is customary to take an aerofoil. Is there anybody who is not knowing what is an aerofoil?
I don't know.
Okay. If you actually take cross section of a flight wing, just a second, let me show you. If you take cross section of a flight wing, that will be an aerofoil. Is it clear?
Yes, sir.
Okay. Even if you take cross section of these particular small vertical stabilizer, small horizontal stabilizer, those will also be some sort of aerofoil. Okay, so what is an aerofoil? Is it okay to you?
Yes, sir.
Yes, sir.
See, aerodynamics doesn't always deal with flight only. It deals with anything moving through air, obviously in high speed. But as this particular thing is first associated with the airplanes, it is customary to have an object which is an aerofoil as my aerodynamic object. We actually have any sort of analysis of aerodynamics using this object only. And the object looks like this, over which the fluid elements are actually moving along streamlines. Now tell me a thing, airplanes generally move through which layer of air?
Stratosphere.
Stratosphere. You are correct. So in the stratosphere, as per our observation, the air is more or less static, right? The
Yes.
airflow is very less, right?
Yes, sir.
So we may actually take a particular thing is that as this particular aerodynamic object, consider it as an airplane right now, okay? Every aerodynamic object we consider as an aerofoil. Let it be airplane, let it be high-speed train, anything. We analyze it, considering it an aerofoil, okay, from now onwards. And not only an aerofoil, but also a two-dimensional aerofoil. Two-dimensional means it is having only this plane, and obviously it has a dimension perpendicular to this plane, right? But that dimension is taken as unit. That is, the dimension is 1. I am showing you that is the final consideration. I think you may know. The dimension along the span is taken as unit. Okay. So that will make every possible equations to be a 2D. And also, what we consider for other cases is that dimension along the other axis, that is perpendicular to this paper to bola jabe na, perpendicular to this laptop screen, is infinite. There is no dealing with that particular direction. So we consider only this XY plane and not two-dimensional aerofoil. That is my consideration. Now let us come to the point. If this particular object moves through air, can we consider there is a relative air velocity from the opposite side? Can we consider this as is shown here as V infinity? If this object moves at a speed of V infinity leftward in a otherwise static air, can I consider that air is having a velocity of V infinity
Yes, sir.
in this particular object?
Yes, sir.
So you may ask
Relative velocity.
why such a consideration is here? Because you know what, as everything of aerodynamics started from airplane only, and in the airplane, the only person who is responsible to measure all these things or analyze all these things is the pilot. So for the pilot, suppose sitting here at the front, he is seeing the air is coming from the opposite direction at V infinity. Yes or no?
Yes.
Yes, sir.
And you know what? An airplane, when it is actually moving, it is actually having a nose up position, a bit of nose up position, as is shown in this particular figure. It is in a nose up position, but it is not moving towards its nose. It is not moving in this nose direction, but it is moving in the horizontal direction. This particular thing is clear or not? Please tell me.
Yes, sir. Clear.
And that is why there is always an angle between the aerofoil and the relative velocity. And that particular angle we call the angle of attack.
Alpha.
You see, this particular aerofoil or the aerodynamic object is actually having a nose up condition. The leading edge and the trailing edge, if we join it, we tell it the chord line, and with the chord line we actually take any sort of angle. The chord line is the reference line of this particular aerofoil, and with the direction of the relative wind, the angle it makes is called the angle of attack. Is it clear to you?
স্যার কট লাইনকে ক্যাম্বার লাইনও বলা যায়?
না, বলা যায় না, ওখানে আসবো চলো। You cannot actually say a chord line equal to a camber line. I will come to this later. Chord line is a straight line joining the leading and the trailing edge, and the angle with this of the relative wind is called the angle of attack. So actually, this particular object is moving forward only. Though the nose is up, it is not moving along this particular line. It is only moving in the horizontal direction. That is why the relative wind is in this direction. So make it clear that relative wind velocity, or the what I have shown here, V infinity, that we call the free stream velocity, is nothing but velocity of the aerodynamic object or the airplane only in otherwise static air. Obviously, the direction is changed. So up to this, is it clear? The considerations are clear or not?
Okay, sir.
স্যার বলছিলাম যে আমরা সবসময় নোজ আপ পজিশনে ধরবো, যেরকম লাইক ইন গাইরোস্কোপি উই হ্যাভ স্টাডিড দ্যাট ইন বিটুইন ইট সুইচেস ফ্রম নোজ আপ পজিশন টু নোজ ডাউন পজিশন মুভমেন্ট অনুযায়ী।
Here I have shown you the general configuration of angle of attack, which is positive. If it is in a nose down position, the angle of attack is negative. Generally, it is nose up position. If it is in nose down position, then we have to consider the angle of attack to be negative. Okay.
Okay. Okay.
Anyway, actually, I have considered this nose up position to make you realize about the angle of attack. Okay. It doesn't necessarily always be nose up, obviously.
স্যার বলছিলাম, হ্যালো স্যার।
Yes, sir. Follow, sir.
স্যার বলছিলাম কি আমাদের ক্লাসে পরে এই স্লাইডটা শেয়ার করবেন আপনি?
আমার পুরো ক্লাসটাই রেকর্ডেড হয়ে থাকছে, টোটাল ক্লাস ইজ গেটিং
ওকে স্যার। Okay, sir. Actually, sir, I was taking screenshots slide wise. That's why I was confused, sir.
No. The total class is getting recorded, and you will get this particular recorded video. You need not worry.
Okay, sir.
I used to share this particular things with you after the class. No problem with this. Okay. You just concentrate on the realization. Every other things you will get. You need not worry.
Okay, sir. Thank you, sir.
And I may assure you, I haven't done many things with the slides. The slides are actually taken from the book of aerodynamics only, that is already shared to you.
Anderson
You
book.
did not take screenshots. Yes, absolutely, Anderson book. Okay, so you need not worry. You just concentrate on the realization.
Okay, sir.
Now, one thing you can be sure is that whenever an object is having some relative motion with air is having only two ways of applying force on the body surface. One is called pressure and one is called shear stress. Pressure is obvious property of air that is actually acting perpendicular to the surface at any point. Any point I take, the pressure force is always perpendicular. And what is the shear stress? The shear stress is always tangential to the body surface and in a direction opposite to the direction of motion. These two things are clear or not? I think pressure is clear. About shear stress, See, the tangential direction can be this, the tangential direction can be this also. So what direction I should take, this or that? Now, if the body is moving in this direction, then the shear stress will be acting opposite to that.
Sir,
That
then
is
it would be
the,
better to say resisting shear force, na?
yes, it is resisting. Shear force is always resisting, cause why the shear force is coming, why the shear stress is developing. I don't know how many of you have come across fluid mechanics. If all of guys have come across fluid mechanics, then they must know that this particular shear stress is developed due to the viscosity.
Yes, sir. As per Newton's law of viscosity, sir.
Yes. So viscosity is always there to resist you, to move something to that fluid, right? So
Yes, sir.
it is always opposite to the direction of velocity. Which velocity? Now there is one confusing part. Which velocity? It is
Relative.
obviously not. Yeah, it is obviously not opposite to the relative velocity. It is opposite to the velocity of the object. Okay. So if you consider V infinity is by default opposite to the object velocity. So shear stress is along the supporting direction of V infinity. Do not mess up in this particular thing, okay? It's sometimes confusing.
Sir, can you repeat the last line?
Yes, obviously. What I told is that V infinity is by default opposite to the object velocity, isn't it?
Yes, sir.
So if shear stress is in the opposite sense of the object velocity, then it is in the supporting sense of V infinity, isn't it?
Infinity. Yes.
So when I say that the shear stress will act opposite to the direction of velocity of the object, somebody gets confused that it is opposite to V infinity, but it is not, man.
স্যার অ্যাকচুয়ালি শিয়ার স্ট্রেসটা যা হচ্ছে ওইটা তো বডির উপরে ইনটেনজেন্সিয়াল ডাইরেকশন অ্যাক্ট করছে, তো সেটা তো বডির মোশনকে রেজিস্ট করবে, সেটাই আমরা রেফারেন্স ধরতে হবে।
Yes. But as there is, as far as velocity is concerned, as here is only we are considering V infinity, na? So it's getting confused by somebody's that it is opposite to V infinity. Sir bolechen velocity opposite, so V infinity opposite dike. So, but it is not that. Okay. You have to make it sure. It is very easy, but you have to know it. Then it won't be confusing. So I think it is clear to you guys.
Yes, sir.
Yes, sir.
Okay. So now I am coming to the next part of action. The shear stress and the pressure distribution in a total obviously is having generated some sort of force and some sort of moment on this particular aerodynamic object or this particular aerofoil. The total shear stress distribution and the total pressure distribution over the total surface of this particular aerofoil will obviously have a resultant force and a resultant moment, isn't it?
Yes, sir.
It is very clear. And we have given them the term R and M as shown in this particular figure. But this particular aerodynamic force is in which direction, that we really don't know. And if we consider in any sort of direction, that will not be beneficiary for us. So what we take is that we may have the resultant force to be resolved in two directions. There is a possibility that we have it along chord line and perpendicular to the chord line. Those are denoted as A and N, those are axial force and normal force. Along the chord line, it is axial force. Perpendicular to the chord line, it is normal force. Some guys say that actually, as the body is not moving along the chord line, it is not necessary, really necessary, to resolve this particular resultant force in N and A direction. But the body is moving along the horizontal line, so along the line of V infinity, obviously. So it is better to resolve the force parallel and perpendicular to the velocity line, and those are actually given as L and D, termed to be the lift and drag. The terms actually very much proficient from their names only. Lift means the force in the upward direction, and drag is a drag that is actually preventing the body to move forward. Because again, you see, drag is in the direction of V infinity, so drag is just in the opposite direction of the object velocity. Up to these, is it clear to you or not?
Yes, sir.
Yes, sir.
Okay. So now our objective, but yes, obviously there is some very well-known relation between L, D, N and A. If we know this particular angle of attack alpha, then there are, with this particular relationship, even if we know normal and axial forces, we can easily know the lift and drag. Okay. So our objective is to go along and find out this particular either N and A or L and D from the pressure and shear stress distributions. Okay. So what we consider here is that we have taken the x-axis along the chord length, and as we have rotated this particular thing a bit, এই particular জিনিসটাকে একটু rotate করে দেওয়া হয়েছে, this particular thing is rotated, so V infinity is also gets rotated, and you see the V infinity right now has not been horizontal, but it is only done for the sake of analysis. Okay. And we have considered another coordinate S that is along the surface of the aerofoil. And after a particular distance, we take a very small length ds, or this is not actually a length, this is actually a curve. But okay, as it is infinitesimally small, we can consider this to be a small length. And as I already mentioned, the thickness is considered to be unit. On the strip, there is a pressure and shear stress. And obviously, if we consider the front view of this particular thing, we get this. On the upper surface, there is a pressure, there is a shear stress. Obviously, the pressure is a function of the upper surface geometry that is given by this AC. The lower surface pressure is a function of this particular lower surface geometry that is given by SL. and these pu, tau u, and pl, tau l, those are actually acting on this particular thing. And if the pressure is pu, what is the pressure force on this particular surface? Obviously pressure multiplied by the area. And what is the area? The area is nothing but ds into 1, that is again coming as ds. So the total force for the pressure on the upper surface is pu into dsu, and total force for the shear stress on the upper surface is tau u into dsu. Obviously for the lower surface, pl dsl and tau l dsl. And if we resolve these particular things in relevant directions, we are obviously going to get their contribution in the normal and axial directions. Up to this, is it okay for you or not?
Yes, sir.
Anybody saying no, sir?
Sir, always the theta will be same for all the four angles.
No, no, no. That is a consideration, and that is a very good question, Saurav. As far as my consideration is there, I should have taken theta u and theta l. But anyway, the Anderson has taken it as theta. But yes, obviously the theta for the upper surface and theta for the lower surface, those are going to be different. You are correct.
Okay, sir.
So if we consider theta u and theta l, that would have been the best. Good question. It is an obvious question. But you guys please have a look at the equations, and I don't think those equations are required to be repeated because those are typically resolved in x and y direction. And in x direction, the force is axial force A, and in y direction, it is normal force N. Anybody is having any problem with the equations? Just see this, giving you time. So may I take this, okay?
Yes, sir.
Yes, sir.
Okay. And obviously there will be a moment acting. We consider right now through the leading edge, and that particular moment is obviously given by this particular equation. You see the first two. The integration is only the integration of the thing. That is not an issue. And the consideration of moment, in general, we consider anti-clockwise to be positive and clockwise to be negative. But for aerodynamics, the consideration is a bit different. Any moment that will cause this particular aerofoil to nose up, we consider positive. And any moment that will require it to nose down, we consider negative. Remember this sign convention, okay? Any moment causing the aerofoil to nose up is positive. Any moment causing the aerofoil to nose down is negative. Is it okay for you or not?
Yes, sir.
Sir, we can remember this as with the logic that nose down situation is not desirable. So we can treat it as negative.
Chandan, my connection got disconnected for a moment. Can you repeat?
Sir, actually, sir, we can treat this sign convention by the logic that nose down situation is not desirable one. So we can treat
No,
as
no, no, no,
negative.
no, no, no. That is not always not desirable one, but most of the time it is not desirable one. Yes, Chandan, are you here?
Yes, sir.
Yes, most of the time it is not desirable one. Don't take it in your mind that nose down condition is not desirable one. Most of the time we need nose up. Okay,
Okay, sir.
but yeah. So you guys please have a look at these particular two moment equations. Those are caused by P and tau for the upper and lower surfaces. And if you are having any particular problem for these two equations, you please let me know. Again, as far as Shourov's query, here also the x and y for the upper surface and x and y for the lower surface point, those are different. Those could have been termed xu, yu and xl, yl, but I don't know why these are not termed, but accordingly that will be put. That I have taken.
And theta also, sir.
Theta also, yes, obviously. So the values of theta, x and y, those are obviously variable for upper and lower surfaces. But even after consideration, if the equations are correct, you please have a look. And if you guys are having any problem, tell me. So I don't think anybody is having a problem, right? Anybody having a problem?
No, sir.
Okay. Anybody requiring more time?
No, sir.
Okay. So if we are having this particular small contribution for this pu and tau u at these particular points, if we actually integrate these things from leading edge to trailing edge, we are going to get the total moment about the leading edge m dash le. And for the other considerations also, as we got this particular small dn and da kind of things, if we integrate those things from leading edge to trailing edge, we are obviously going to get the normal and axial forces on this particular aerofoil surface. I think it is very clear to you. Now I am coming to the actual considerations. Have you guys noticed about those dash, n dash, a dash, m dash le? Don't you guys are having any problem that why these dashed are here?
Yes, sir.
Yes, sir. Very.
See, aerodynamic guys, they are very much alarmed about the assumptions. Okay, very much, because aerodynamics is very much affected for assumptions. So they used to take the assumptions in the notifications also. In this particular case, we have considered a unit depth of this particular aerofoil section, right? The span is unity as it is told, but in a practical case, is it unity always? It is not, obviously. So these particular considerations are valid for these per unit span or per unit depth analysis, and that is why to denote it there is a dash on every possible force and moment. Okay.
Yes, sir.
Sir, what is span?
What is dash means? There is n prime and a prime, na?
No, span. What is span?
Span is this particular depth, what is shown here as 1.
Okay.
Okay, that we call span of an aerofoil. Obviously a 3D aerofoil, but here we are considering 2D. We are not considering there will be any sort of implication of this particular span on our analysis, and that is why each of our analyses are going to be 2D right now, and for any sort of such analysis we are having this particular dashed. Now you will tell me a thing, how to actually move on with these particular integrations. Are these going to be very easy?
No, sir.
These are obviously going to be tedious. And also for getting these equations solved, what we require is that we obviously require to know the distribution of pressure and shear stress along the upper and lower surfaces, isn't it?
Yes, sir.
If you do not know PU as function of SU and PL as function of SL and also the taus, how are we going to actually solve these particular equations? There is no way we can actually solve this out. So the researchers started thinking of that, how are we going to get these particular pressure and shear stress distributions? And for most of the time, the one and only possibility of getting these particular pressure and shear stress distributions are actual experiments in the wind tunnel. What is a wind tunnel? In a wind tunnel, how many of you guys are actually accustomed with the term wind tunnel?
I have an idea, brief idea.
Okay.
Sir,
So,
is it an experimental setup to measure velocity or, I mean, a model type of model?
yes,
Or
absolutely. In a wind tunnel, small aerofoil models are tested. The aerofoil model is obviously kept static and air is actually blown on it at different velocities in order to find out the interaction between the air and this particular object, and obviously the with pressure sensors and stress sensors the pressure and shear stress distribution can be obtained. That is purely an experimental setup which we use to get this particular pressure and shear stress distribution data.
Sir, in wind tunnel, what is the working fluid, sir?
Air, তাই
Okay,
জন্যই
sir.
তো উইন্ড টানেল রে ভাই। Wind is associated with air, na? It is high speed air, that is why it is called wind tunnel. And
And here, sir,
nowadays,
as you mentioned that, sir, here in this experiment, sir, aerofoil object is set up at in static condition, is it?
yes, because you actually cannot move within the wind tunnel and aerofoil at a particular velocity. It is very difficult. So aerofoil is kept static, wind is flown on it. Just the opposite case in the stratosphere. In the stratosphere, airplane is moving, and in the wind tunnel, just the opposite thing is occurring, but the similar condition is getting simulated. Similar condition is there.
Okay.
The object moving through air or air moving over the object will cause the same interaction. There is no problem. And there is a second possibility. Can you predict what? One is obviously experiment through the wind tunnel, get all these particular data, and then integrate it up. That is a possibility. And there is a second possibility nowadays. Can you guys predict?
Sir, can we not assume that pressure and shear stress distribution, pressure and shear stress is uniform in order to simply make
we
it
cannot,
integration?
we simply cannot. For the case of airfoil, we simply cannot. That is very much different from point to point. Very much different. We cannot consider it uniform. But yes, there is a second possibility nowadays. Instead of testing in a wind tunnel setup, which is really very costly, in JU we are having one wind tunnel. We have some aerofoil setup also there. If possible, obviously in your course of action of studies, once you be there, maybe after some times, I will show
Sir,
you, no problem.
you are right, sir. Actually, in this same, sir, one wind tunnel experiment is there, sir, in PG lab curriculum.
Yes. Anyway, that is all right. One thing is that this particular wind tunnel setup is really costly, and that is why people have found alternatives of these particular experimental observations. And what I actually inquired from you is that, can anybody predict what can be the alternative?
The computer simulation.
Yes, obvious. And the subject of computational fluid dynamics actually allows us to get on with this particular thing.
CFD.
Applied mechanics, CFD, absolutely. Applied mechanics, guys, it is very similar to the one you take as finite element analysis. The finite element analysis is the analysis of solid bodies in small elements, and CFD is computational fluid dynamics that actually have elemental fluid spaces to analyze it further. I am not going in the details of CFD because you guys are already having finite element analysis or CFD as your separate subjects. But the computational analysis allows us to simulate the airspace, the moving airspace over this particular object, and to predict the pressure and shear stress distribution on this particular thing. A very useful software for this particular analysis is obviously ANSYS Fluent. I think anybody associated to fluid mechanics or applied mechanics specialization should know this particular software by this time. ANSYS Fluent ta bodhoy shobai jane. I think ANSYS Fluent, at least the name is known to you.
Sir, yes, sir, name is known to you, but not anything in depth about.
Not the use is known to you, Chandan, but okay, no problem. I think by the time you actually end up your masters, the use will be also known to you, most probably. Is it clear the two ideas, that one is the computational domain and one is the experimental domain? In these two ways, these particular integrations and analysis are being done. Okay.
Okay, sir.
Now, what you guys think? Which particular analysis is more important? Sorry, more accurate. The experimental domain analysis or the computational domain analysis?
Sir, experimental.
No, sir, I think
Absolutely.
computerized analysis is the more accurate, because on this process we can give the input in the exact manner.
But sir, actually, sir, in C,
No, Devashish.
sir, in C,
The computational domain analysis is
actually, sir, in CFD, we have
yes
to
or no?
do some programs, some algorithms, and there is some approximation, sir. And as due to approximation, sir, some error will be there.
Absolutely, absolutely, absolutely. And actually, obviously, in computation, there is no problem in the computation field only, but obviously, in terms of predicting this particular pressure and shear stress, we actually use some common algorithms, and those are having their assumptions in them. And that is why computation and analysis is not always perfect, but experimental analysis is. I may cite you a simple example. Okay, simple example. That is not of flying airplanes, but for other aerodynamic objects. Have you guys seen the Formula One cars?
Yes, sir.
And those cars are also having aerodynamic design. Was anything moving through air at high speed? Aerodynamics always come in consideration. Obviously, for low speed vehicles and all this, the interaction of air is not very important always, but for any high speed vehicle like high speed trains, high speed cars, high speed anything, those comes under the purview of aerodynamics. So the Formula One cars are obviously designed using such techniques of minimizing the drag, because it is the drag, as I have already shown you, that it is the drag that is actually resisting you from moving forward, resisting the object from moving forward. So there are obvious aerodynamic analysis to reduce this particular drag. Okay. Now you see, if you actually see the Formula One racing, all the cars looks more or less equal, isn't it? সবগুলোকেই দেখতে কাছাকাছি একরকম লাগে তো না? But still, some companies like Ferrari, Mercedes, McLaren, they are always going to be the winner, and some companies like Cosworth, Marussia, they are always coming in the last or second last or like this. So don't you guys actually think of that, what is the problem in these particular cars? The drivers are more or less okay. One driver actually moves from this team to that team. But even if the driver is actually driving that particular car instead of a premium company car, he is not having that particular speed. Now, why this is happening? All the cars are looking similar to me, but why some cars are better, in which respect some cars are better. That is the case that those companies which are having the first, second, third positions are often having a wind tunnel on their own, and they can actually observe experimentally every possible force on their car, and they can design it accordingly. But for the companies who are not having a wind tunnel on their own, they mostly rely on the CFD analysis, and using the CFD analysis they design their car, and the difference is well known to you. Some companies always win and some companies always are the back runners. Is it clear to you? That is very, very important
Yes, sir.
to actually predict what is the difference between the computational analysis and the actual analysis. And companies which are mid runners and companies which are front runners, the difference is that, as one of you actually told na, ke bollo je the model analysis part, some guys can have a small wind tunnel in which they can actually test the smaller model of this particular car and get everything done. Some companies, which are obviously very rich companies, they can even have some wind tunnel within which the life size of the particular car can be tested. The airplane companies like Boeing, Airbus, nowadays they are actually doing some life size analysis of their wings. Life size analysis means the actual model is of the same size of the actual product. It is not a scaled down model at all.
Model and prototype both are same. That means, sir,
একদম model prototype both are same.
no scaling factor is there.
তাহলে তো
No
বিশাল
scaling
বড়
factor is there.
time লাগবে।
একদম ওই যেটা বলছিস বিশাল ব্যাপার, সেরকম বিশাল বিশাল উইন্ড টানেল আজকাল তৈরি করেছে। Those are very costly, but obviously they are finding it worthy because all the data they are having are actual data, and they are not requiring to proceed further with any of assumptions and computations. So that is the difference between testing and computation. Okay. So up to this, is it clear to you guys or not?
Yes, sir.
Okay. But as this, just give me a second. A phone call is coming. Just give me a second. Okay. Uh, so if up to this it is clear, then I may come to the next point, is that for model analysis, we obviously require some Am I audible to you?
Yes, sir.
Yes, sir.
Sir.
Okay, I think my connection got disrupted in between. So for every sort of force and moments, we have some sort of parameters which will make this non-dimensionalized. So instead of lift, drag, normal force, axial force, we are having their corresponding coefficients. Obviously, how to normalize a force? Obviously, you have to divide it with some other force. And that force is taken as Q infinity into S. What is Q infinity? And Q infinity is defined as the dynamic pressure that is actually shown to you half rho infinity V infinity square. I think all of you guys are actually accustomed to Bernoulli's theorem. এই
Yes,
থিওরেমটা
sir.
প্রত্যেকে জানে তো?
Yes, sir.
So Bernoulli's theorem says P plus half rho V square is constant for a constant elevation. And this half rho V square is nothing but a term of pressure, and that we call the dynamic pressure. And for this particular aerodynamic model, as V infinity is the free stream velocity, rho infinity we say the free stream dynamic, the free stream density, and Q infinity is the free stream dynamic pressure. Is it okay to you?
Sir, what is S?
Yes, I am not getting you.
Sir, what is S? S. Platform area, it is written there, sir.
Sorry, can you repeat once?
Sir, what is S? S. Sir, L divided by Q infinity multiplied by S. What is S?
You know the S is actually shown in the next figure.
Question number 2.
That
Yeah, why do we need,
if we take the
why do we need energy?
top view of the two wings of an airplane, top view of the two wings without the body, okay, the total area you get is the area S, and that we say the planform area. So A is clear to you?
Yes, sir.
Okay. The chord length C is already clear to you. If we take a cross section anywhere in this particular wing, we are obviously going to get an aerofoil, and the leading and trailing edge joining line will be the chord, and this is the chord length. You see, for an actual wing, the chord length will vary along the span. Is it clear? দেখে বোঝা যাচ্ছে? The chord length will vary.
Yes, sir.
Yes, sir.
Near the body of the
But in the second figure, in figure B, sir, it is shown as a circle, sir.
the aerodynamic object can be an airplane. Then the cross-sectional, then the reference area S is this platform area. If the aerodynamic object is your cricket ball, then the reference area is again the platform area of this particular cricket ball, and that is pi r square. So the object you are dealing with, that will actually define what is your reference area. Is it clear to you?
Yes, sir.
Yes, sir.
Okay. And what is your reference length? Obviously, reference length is required only for the moment. You see, for the airplane case, it is the chord length, and I must say it is the mean chord length, because the chord length will vary from the tip to the hub. That is, near to the body, the chord length is higher, and to the farthest point, the chord length is lower. So that should be the mean chord length. And for the circular body, that is the diameter. Okay. Is it okay to you?
Yes, sir.
Now you see, every possible coefficients are given in capital letter, right? CL, CD, CN. All are given in capital letter, right? For our case, this is our object. What will be the reference area, man? কি মনে হয়?
Sir, rectangular strip.
मैम क्या
আর একবার শুনতে পাইনি।
Rectangular strip.
What is your perception? What can be your reference area?
मैम फोन नंबर क्वेश्चन क्या था
rectangle.
Sir, the surface area of the wing.
Sir, is it the projected area?
Yes, it is the projected area, but looking from front view or top view?
Top view.
Sir, front view.
না, front view টা ভুল বললি। As for the
Top view.
airplane wing, we take the top view. Projected area is correct. The projected area from the top view. And what is the projected
Okay,
area
sir.
from the top view?
So rectangle.
Correct, you are rectangle. What is the area? বলতে পারবো easy.
S into unity L. L is taken as depth. So and L is unity.
এই ওটা
So
L নয়, ওটা 1.
oh আচ্ছা আচ্ছা so S into 1. S.
S into 1 হবে কি? ভেবে বল।
না না এস এর সাথে এস
is
cos
not-
theta
C
Yes,
is not shown here.
Sir, we have to take the differential.
যদি ওপর থেকে নিস, there is a rectangle না?
হ্যাঁ
And the rectangle এই সাইডটা কত? This is nothing but the chord length C.
আচ্ছা আচ্ছা কর
Oh আচ্ছা আচ্ছা হ্যাঁ chord length yes.
Yes. So the reference
see.
area will be C into 1. Okay.
Yes sir.
And what is the referent length? That is the chord length C again. So for this particular case, you see the reference area is C into 1, that is C. And the reference length is also C. So you see the three small letter items are written CL equal to L dash by Q infinity C, CD equal to G dash by Q infinity C, and CM equal to M dash by Q infinity C square. Those are given in small letters to readily denote that these are there for 2D cases, per unit span cases. Those are not actual. Is it clear to you how in aerodynamics every sort of things are getting denoted separately? In the previous slide, everything was in capital because those were actual data. Here for our case, everything are in small because these are per unit span data or 2D analysis data. Okay. নিচের দিকে তিনটে দেখবি। So is it okay to you?
Yes sir.
okay sir
Obviously, there are some other coefficients called the pressure and skin friction coefficients. Those are okay. Those are nothing more serious. And one thing that I actually forgot to mention is that what is this particular free stream condition means. You see, what I actually told the free stream velocity, that is the velocity of the air relative to the airplane or my aerofoil, right? Now, if you are going to take the velocity of air very close to my object, are you going to get the actual velocity?
No sir, there will be boundary layer.
There will be boundary layers, there will be disturbances, right? So the free stream velocity is actually taken a bit away from my actual object. Then my actual data I will have. And as you are having this particular dynamic pressure, rho infinity is also denoting that the density of air is also taken a bit away, because nearest points to the object, the properties can be changed due to disturbances. So so the free stream conditions are a bit away from the object. Okay. So as we are having all in the coefficient forms, all sort of things in the coefficient forms, we are obviously going to have this equation and this equation in coefficient form. If we actually divide both the sides with corresponding normalizing factors, q infinity c square and q infinity c. And after normalization, this particular thing actually comes in picture. Obviously, ds, the small ds, is now resolved in dx and dy. And then from those particular two moment and force equations, they are getting dimensionalized, non-dimensionalized in term of this. And for our analysis, instead of using direct moment or forces, we prefer to use these non-dimensional moment coefficients and force coefficients. Because these will allow model analysis to be done. If we actually test a small model of an airplane in a wind tunnel and get these particular force coefficients and moment coefficient, the same particulates we can actually use for the actual airplane also. Obviously, if other conditions are prevailing. Is it okay to you?
Yes, sir.
এই কি বললো রে, শুনতে পেলাম না।
Yes, sir, it is okay.
Okay. So as I mentioned that we can use these particular things if other conditions are prevailing. Obviously, the other conditions must come in picture. Before that, this is a general characteristics of drag and lift coefficients. আচ্ছা একটা কথা, drag and lift coefficient can be very easily found if we find the normal and axial force coefficients using these two equations. এটা আগেও দেখিয়েছি, okay? Was the relationship between lift and drag and relationship between the coefficients, those are obviously same. So if we find out Cn and Ca, we can obviously find out Cl and Cd. For the actual airplane cases, the lift coefficient and drag coefficient vary with the angle of attack in this way. It actually increases with angle of attack up to a certain decreasing rapidly. For CD, it is more or less constant, and for high angle of attack, it increases. These are actual wind tunnel data for CL and CD with respect to angle of attack. Okay. You see, even for a zero angle of attack, you may have a positive CL. And if the angle of attack is negative, then also for some time CL is positive. Beyond some point, for negative angle of attack, CL is going to be negative. Is this particular thing clear to you guys or not? কি রে
Yes,
কেউ
sir.
সারা শব্দ করে না রে?
Yes, sir.
Is it clear to you or not?
Yes, sir.
Yes, sir.
Okay. Today enough teaching is done. Let me tell you some practical stories. One practical story. I think that will be nice for you. So from this particular curve, are you seeing that you cannot actually increase the angle of attack more and more and more and get the CL to be increased more and more and more. Up to a certain point that will increase and then this will decrease so rapidly that if we actually go beyond this sort of angle of attack, it will be very difficult for the pilot to control the airplane at all. And this particular phenomena we called stalling. STALLING.
What's that? Installing.
Stalling. STALLING. লেখা আছে বইতে, চিন্তা নেই।
It's the same phenomena happening in axial flow compressor, na?
Yes.
Axial flow compressor. Same phenomena happens.
Stalling means, in English, stalling means it is gone. Okay. So in case an airplane actually have the condition of stalling, it is very difficult to rescue it actually. আচ্ছা বেশ, একটু গল্প করা যাক। Can you guys remember Malaysian Airlines 747?
Yes, sir.
What happened to that particular airplane?
জলে ডুবে গেছিল।
তো ফ্রম দ্য এয়ার তো আর জলে ডুবে যেতে পারে না, তার মানে আগে ভেঙে পড়েছিল, তাই তো?
Yes, sir.
Now what happens if you guys are actually boarding an airplane? You sometimes see that the pilot will actually ask you to keep the seat belt on and say there are some possible turbulence in between, keep your seat belt on, and the airplane starts vibrating a bit. What happens in turbulence? You see the relative velocity V infinity that I actually have shown you. V infinity is exactly equal and opposite to the airplane velocity that will occur in the stratosphere only, na? Where air is otherwise static.
Yes, sir.
But in the troposphere, where there are turbulence, there are wind gusts, there are thunderstorms, will this V infinity be exactly equal and opposite to the airplane velocity? হতে পারে? The air velocity is already there.
না স্যার, হবে না স্যার।
তাই না? And if the air velocity is having turbulence, then can I say that this V infinity also changes from this moment to that point? In a turbulence, obviously the air velocity is changing every time, right? It is not constant. So V infinity won't be constant, isn't it? V infinity is what? Actual velocity of air at that moment minus the velocity of airplane. এরকম কিছু একটা হবে। The relative velocity of air with respect to airplane. So if the air velocity is having turbulence and it is changing every moment, V infinity will also change every moment, isn't it?
Yes, sir.
Yes, sir.
Yes, sir.
And you see, all your force and moment coefficients are depending on this V infinity. And your airplane design is actually on this particular V infinity design. Because with all these coefficients that is designed. So if V infinity is changing always, your CL and CD are going to change always, isn't it?
Yes, sir. As they are function of the infinity.
Yes. So if these are changing each and every time, the total aerodynamic force is changing on the particular airplane.
Yes, sir.
And what happens to a body when you are actually keeping it in ever-changing forces? That will start vibrating, isn't it?
Yes, sir.
Dynamic
action, sir.
And that is what happens to your airplane in turbulence. That will start vibrating. Okay. And in a very, very unfamiliar course of action, suppose it happens that in a turbulent storm, your wind velocity is more or less in the same direction of your airplane velocity. That will decrease V infinity drastically, isn't it?
Yes, sir.
Yes, sir.
And I may assure you that this drastic reduction of V infinity will cause in a drastic reduction of lift force. That we will come later. But the lift force is very much associated with V infinity. If V infinity is not there, if the relative velocity is not there, it is difficult for the air to interact with your airplane. So the resultant force will be very less and the lift force will be very less, and momentarily the lift required for the airplane to keep in that particular elevation may not be there. And it happens sometimes that due to this particular phenomena, the airplane suddenly comes down a bit. At which elevation it was in, it suddenly comes down. If the pilot is not very alert, that may cause problem. And those particular points we call the air pocket. Air pocket actually occurs in turbulence, in thunderstorm kind of things, where the velocity of air is in the direction of the velocity of the airplane, thereby reducing V infinity very rapidly, thereby reducing the lift force very rapidly, and air pocket will form. কথাটা বোঝা গেছে কি?
স্যার একটা প্রশ্ন ছিল।
বলো স্যার।
স্যার বলছিলাম এই যে বললেন এয়ার পকেট এই ফিনোমেনাটা যেটা হচ্ছে মানে টার্বুলেন্স আর এই ব্যাপারটা নিয়ে মানে ভি ইনফিনিটিটা ডিক্রিজ করে যাচ্ছে, ভি ইনফিনিটিটা, তো এটা তো ট্রপোস্ফিয়ারতে হচ্ছে, কিন্তু স্যার এই স্ট্র্যাটোস্ফিয়ারতে ভি ইনফিনিটিটা ভ্যারি করছে না, ফিক্স থাকছে। ভি ইনফিনিটিটা স্ট্র্যাটোস্ফিয়ারতে ফিক্স কেন থাকছে?
একদম স্ট্র্যাটোস্ফিয়ারে চলে গেলে কোনো সমস্যা নেই। Each and every problem with airplane, each and every accident with airplane occurs in the troposphere only.
স্যার আমার প্রশ্নটা হচ্ছে ভি ইনফিনিটিটা স্ট্র্যাটোস্ফিয়ারতে ফিক্স কেন থাকছে স্যার? এটা ট্রপোস্ফিয়ারতে,
as your friend have already told that in stratosphere the air is more or less static. In stratosphere no thunderstorm occurs, in stratosphere no wind gust occurs, the air is more or less static. Okay, that's
sir.
why airplanes prefer moving through stratosphere.
And sir, what about the sir plane velocity that is in the control of hand of pilot, is it now?
In the stratosphere also the flight velocity is in the control of pilot. It may be in autopilot also, that will come later, but once it is in the stratosphere it is more or less safe.
And actually the problem of the phenomena of reducing of V infinity is due to the fact that air velocity and the flight velocity both are in same direction. That's why V infinity is reducing.
Yes, mostly.
And in turn it is affecting the resultant force and lift force.
Yes.
In adverse manner.
Yes.
And so-called air pocket phenomenon is happening.
Yes, and those particular things obviously occur in troposphere only.
Troposphere, because there is turbulence and storm like things are there.
Turbulence in troposphere.
Okay sir, okay sir, got your point sir.
Now as I came to this point, what happened to that particular flight, I have my personal ideas. Okay, having all the things done, I have heard about all these things. What was actually instructed to the pilot by the ATS or the air traffic signal authorities, they actually instructed to move up 5,000 feet in a very stormy condition. They informed Mr. Pilot, you are going to face a very stormy condition. You cannot actually move through that particular thing with your airplane. So it's better you move up 5,000 feet to bypass this particular stormy condition. Okay. একটু কর মানে ইন্টারঅ্যাক্ট কর, না তো বলা যাবে না।
Okay sir.
But as per my perception, the air traffic control as well as the pilot, maybe there was a bit of delay in communication, maybe, I'm not sure. But when the pilot actually started moving up this particular 5,000 feet, the thunderstorm was already negotiated. I think by the time he should have moved up, there had been a bit of delay, and such a bit of delay can cause a huge problem. Because under the thunderstorm, under the turbulence, this particular curve, that with angle of attack up to a certain limit, CL will increase. The limiting CL might have come earlier. Suppose this angle is 20 or 21 degree, in a stormy condition that can be reduced to 15 to 16 degree, and from this point these may come down. So under the stormy condition, as the pilot tried to move up, increasing the angle of attack with a nose up condition, that might have caused a total stalling of the airplane. And as I have already mentioned, once it is stalled, it is very difficult for the pilot to control it further, because the lift drastically gets to zero, and it is a free fall. And it is very difficult. See, if the lift is zero, it is a free fall, isn't it, under its own weight?
Yes.
And
Yes,
by
sir.
that time, it is almost impossible to control it again. And for a huge airplane like this particular Boeing 737, it is obviously very difficult. Small aircraft of fighter planes, small jet planes. I have seen a video. I am not sure about how much correct the video is, how much real the video is, but I have seen once the pilot could have retrieved it. Obviously, an Air Force pilot, the most efficient pilots of all, and the airplane was very light. But I'm not sure if the video is real, but that was the only circumstances I saw that even after almost a free fall, the pilot could control it. But for every other cases, that could not be controlled.
স্যার একটা কোশ্চেন ছিল।
বলো স্যার।
হ্যাঁ স্যার বলছিলাম এই কার প্লট থেকে তো দেখা যাচ্ছে কি মানে after a certain angle of attack, when CL maximum limit is reached, then when we further increase angle of attack, then it is observed that lift coefficient is decreasing, and that time we are saying that thing is stalling phenomena, and simultaneously we are seeing from the plot that is the drag coefficient is also increasing, sir.
Yes.
So sir, stalling can be termed as the decrease in lift coefficient and increase in drag coefficient.
See, as far as stalling is concerned, it is not associated with drag coefficient at all. Yes, the drag coefficient is increased, but still when the lift coefficient is getting to zero, that is our most of the concern. Okay, drag
Okay, sir.
coefficient ওইটুকু বাড়লো বা কমলো ওটাতে আমাদের খুব কিছু যায় আসে না actually. The engine power may be required a bit more, but that won't cause me a real problem. But the stalling is there due to the sudden decrease of lift coefficient only. Is it clear?
Sir, that means lift coefficient is going to lift force is going to going on decreasing and decreasing and reaching zero, and
Yes,
in
yes.
turn the weight
Absolutely. After this point, it will suddenly go to zero.
and it is going to zero, and in turn weight is coming into picture. So ultimately free fall of the body is happening.
Yes.
Airplane is.
Yes.
Okay, sir.
Okay, so up to this, it is clear. Whatever I have told today, anybody is having any query, please.
Sir, when the angle of attack is zero, why is the CL positive?
That I will answer in the next class.
Okay, sir.
Because the aerofoil is actually not symmetric. You see, the upper and lower surfaces are not symmetric. If those two surfaces are symmetric, that is for a symmetric aerofoil, the angle of attack will be zero, or a zero lift coefficient. If it is symmetric, then CL will be zero at zero angle of attack. As there is an asymmetry in the design for airplanes, that is why there is a small positive CL even for zero angle of attack. Okay. Anything else?
No, sir.
স্যার বলছিলাম, হ্যালো,
হ্যাঁ বলো।
বলছিলাম এই যখন লিফটটা পাইলটটা ড্রাইভ করছে, যখন দেখছে স্টার্লিং এই লিফটটা ফোর্সটা জিরো হয়ে যাচ্ছে, স্টার্লিং কন্ডিশনে চলে আসে, তখন স্যার পাইলট কি এমনি ড্রাইভ এফার্ট করে নাকি, মানে লিফটটা ফোর্সটা কিছু মানে অপারেশন করে মানে লিফটটা ইনক্রিজ করা যায়, ফ্লাইটটা উপরে নেওয়া যায়, এরকম কিছু?
স্টলিং হয়ে গেলে খুব ডিফিকাল্ট। Only the pilot can try to have the engines running so that it will again come in a picture, but it's very difficult. Free fall এ কি করে করবে, খুব difficult.
Because gravity is coming into picture.
Yes. See, gravity is always there in the picture, but lift is actually taking care of the weight. But once lift is zero, gravity is alone.
Yes, sir.
And once it is under gravity, it is very difficult.
Before stalling, sir, lift was predominant over gravity, but as stalling condition is reached, sir, there is no lift force, so ultimately under gravity free fall is happening.
একদম free fall is happening. Anything else?
স্যার বলছিলাম এই স্টলিং কন্ডিশনটা আমরা পড়েছিলাম এই অ্যাক্সিয়াল ফ্লো কম্প্রেসরতে, ওই স্টলিং আর এই স্টলিংটা ডিফারেন্ট আছে?
Yes, I think so.
যে কোনো কিছুই যখন a particular thing যখন একটা লিমিটিং কন্ডিশনে চলে যায়, তাকেই স্টলিং কন্ডিশন বলা যায়, after which it cannot be operated. Okay. Axial flow compressor ও তাই। That is the limiting condition. You cannot go beyond it. Okay. Anything else?
No, sir.
Okay. Then when should we meet for the next class? I am stopping the recording, okay?